Welcome to Homework Lib.
Hi, so before we begin with this problem, let's review some of the basic concepts of rotational spectroscopy. Let's recall that the rotational energy for a rigid rudder approximation, it is going to depend on the angular momentum, that is J, and on a rotational constant. So this is my rotational constant. And this is the dependence that we have with both of those variables. We also know that in rotational spectroscopy, the selection rule coming from quantum mechanics, it is going to be the change of angular momentum needs to be equal to 1. So if we start at j equals 0, the only possible final state that we're going to have is j equal 1. Replacing this part for a change of energy, this means that the change of energy that we are observing is coming from starting at j equals 0 and ending at j equals 1. We have this equation, so the change of energy is going to be 2 times the rotational constant when we replace the value for j equals 1. Now, that rotational constant depends on the moment of inertia of our molecule. And in the case that we have a diatomic molecule, the moment of inertia is simply the reduced mass times the equilibrium distance squared. This is just the definition for the reduced mass, and the value for R, it is going to depend on the atoms that we have. So in this case, this is going to be carbon, and this is going to be oxygen. Thus, if we replace delta E with 2 times the rotational constant, the 2's are going to cancel out, so we end up with h bar squared divided by I. Okay? Now, with this information, since we know that the change of energy is h bar squared divided by the moment of inertia, we simply can calculate the moment of inertia as h bar squared divided by delta E. The information that we're given is just the change of energy that corresponds to that wave number of 3.84 centimeters to the minus 1. This value, we can convert it into the International System of Units, and you're going to find that the value is going to be 7.627 times 10 to the minus 23 joules. And the value for h bar in atomic units is 1.05457 times 10 to the minus 34 joules second. Okay, so far so good. So now the only thing that we need to use is replacing these values into our equation. 1.05457 times 10 to the minus 34. This is going to be joule squared second squared. Remember that quantity needs to be squared. Divided by the energy that I have, 7.627 times 10 to the minus 23 joules. The final result is going to be 1.458 times 10 to the minus 46 joules second squared. And this is going to be our first result. This is going to be our moment of inertia for our molecule. So here you may think that maybe this value is very, very small, but recall that that moment of inertia corresponds to a reduced mass times radius squared. And that reduced mass, when we transform it into kilograms, we're going to have a very small value. And also the value for the equilibrium distance, we expect it to be around of 1.2 angstroms. That is 1.2 times 10 to the minus 10 meters. Okay? So now, the next step in our problem is to find the equilibrium internuclear distance. And for doing that, we're going to use this equation. But first, we need to calculate the reduced mass. Here, the reduced mass is mass 1, m2, divided by m1 plus m2. Thus, in the case for carbon, this is 12. For oxygen, is 16, divided by 12 plus 16. And this is in atomic mass units. the result that we're going to end up with is 6.857 atomic mass units. Now, since we're working in the International System of Units, then we need to convert that recalling that one atomic mass unit, or 1 Dalton, corresponds to 1.66 times 10 to the minus 27 kilograms. So our result for mu, it is going to be 1.138 times 10 to the minus 26 kilograms. Here we're working in International System of Units, but you may want to do everything in atomic units. Just remember that one atomic mass unit is not equal to the mass of electron. And if you want to use atomic units of energy and everything else, you would need to transform this value that is given in the periodic table to the correspondence into ME, which it turns out to be 1,880 something. I think it was 1,822.89. But it doesn't matter right now because we're not using it. That's just a comment for in the case that you want to use those units. So with this information, we know the moment of inertia, we know the reduced mass. So from here, the value for r, the distance is moment of inertia divided by mu. This is going to be the square root of 1.458 times 10 to the minus 46. This is joules second squared. Divided by 1.138 times 10 to the minus 26 kilograms. Now, just to verify that the units are correct, let's recall that 1 joule we need to find the units corresponding to this operation. So 1 joule is nothing but kilogram times meter squared times second to the minus 2. This is multiplied by second squared divided by kilograms, and everything to the 1/2. Kilogram and kilogram cancel out, second to the minus 2 cancel with second squared, and we end up with meter squared to the 1/2. So this is going to be in meters. Okay. So with that out of the way, we can proceed with our calculation. And the answer that you're going to find is that this is 1.1319 times 10 to the minus 10 meters. Or, which is the same, 1.132 angstroms. And that would be all for this problem. Just remember, the final answers are going to be this distance in whichever units are required of you, and this moment of inertia.